All right, in this video we're going to keep investigating converging lenses. If this is the first video you watched over converging lenses, go back and watch the one previous to this. It's got a lot more information. But in the last example we did, we put the object farther away from the lens than the focal point. In this one, I'm just going to move the object here closer to the lens than the focal point. Okay, let's do our ray tracing. I'm still going to pick out the tip of the arrow and allow rays to propagate out from that. I'm going to pick out one ray that propagates parallel to the horizontal axis. I know what that's going to do because I look at my ray tracing rules. That's going to propagate through the focal point like this. And I'm going to notice I had another rule which said light entering the lens through the focal point on the same side, but that clearly won't work here because any light propagating through that focal point is not going to enter the lens. So by moving the object over here, I can't use that rule. I have to use the other one which says light passing through the center of the lens is not deflected. All right, that actually worked out okay. It's always suspect when I'm drawing things with Sharpies or drawing things with anything. It looks like these rays are never going to meet. That actually turns out to be true. These rays diverge. If I move the object closer to the lens than the focal point on the same side, the rays will diverge over here. Now, does that mean I don't see anything? Well, the answer is no. So what I need to do to see something, because I mean you guys have all looked through magnifying glasses, you know that you're going to see something. I think I'm going to have to supplement my paper here. Let me do this. What I'm going to have to do, let me trace these back so you can tilt it so I can actually see to draw. I'm going to take these rays and trace them back. Now, when I trace them back, light is not actually propagating in this region. Oh good, I got it. Light is not actually propagating over here. I mean, there might be some light, but these rays are not actually propagating in this region. These rays are over here going off to infinity, getting farther and farther away from each other all the time. Back here, that's why I've drawn these as dotted lines. We're going to call these virtual rays. The upshot of this is if I'm over here looking, I see an image that appears to be formed by these rays, but there's actually no image formed by these rays. The image is formed by the virtual rays. So I'm going to find the point of convergence, which is right there. Again, I'm going to realize that this came from the tip of the arrow, and so the tip of the arrow is right there. So my image now looks like this. Here's my object, here's my image, here's my focal point. Okay, fair enough. Well, let's take care of the obvious one first. If this is not formed by real light rays actually propagating where the image is, if it's formed by these virtual rays, I'm going to call this a virtual image. We saw in the last video that a real image can be projected. This one cannot. You cannot project this image if you move the object closer to the lens than the focal point. All right, let's run the mathematics and make sure this lines up. Let's say that my distance to the object is now 10 centimeters. My focal length is 15 centimeters, right? It's got to be farther away, it's got to be bigger than the distance to the object. And I'm going to find the distance to the image and the magnification. All right, I have my thin lens equation. I'm going to write it down in this form. D to the image is equal to F DO DO minus F. In this case, that is FDO. I'll get 15 centimeters times 10 centimeters divided by 10 centimeters minus 15 centimeters. So I'm going to get, notice, a negative sign for this. I get 150 square centimeters divided by negative 5 centimeters. I lose 1 centimeter on the top and 1 on the bottom. And I get that my distance to the image is negative 30 centimeters. All right, let's see if this matches up at least qualitatively with what I drew. Well, this is farther away than the focal length and the distance to the object, so that is a check mark. No big deal. Again, if I got out a ruler and measured it, I probably wouldn't find the ratios are right, but I'm just looking qualitatively. Unless you have an actual diagram of an actual lens and you're using a straight edge and being really, really, really careful, which I would always encourage you to do. Use a straight edge and be really, really, really careful. You're still going to probably have to look at it more qualitatively than quantitatively. We're just looking for the behavior of my ray tracing to line up with some mathematical predictions. So what does the negative mean? We saw in the magnification equation, negative tells us that the image is upright, but this is not the magnification equation. For a converging lens, a negative image distance tells you that the image is on the same side of the lens as the object. And in the last example where we had an object over here, I had a positive image distance. So for a converging lens, and only for a converging lens, negative image distance tells you, I should say only for a lens, negative image distance tells you that the image and the object are on the same side of the lens. Let's look at the magnification. Negative di over do. So keep track of this negative sign. This is from the definition. I get negative from here, and then negative 30 from here. Negative 30 centimeters over distance to the object, which is 10 centimeters. So the two negatives are going to make a positive. I get a magnification of 3, which tells me it's positive, so my image should be upright. It's bigger than 1, so my image should be bigger than my object. Check, check. Upright, bigger than my object. So I feel good about this. And this is a general result for an object that is moved closer to the lens than the focal point. Now, let's just for kicks, let's ask ourselves the question, what would happen if I put the object at the focal point, right? So this is a different problem. Forget all the purple drawings and just look at the green ones. What happens if I do that? Well, ray tracing, I could still ray trace it. Might be some strangeness going on. What you're going to find, though, is that, well, here, you know what? Let's just do it. Let's see if I can actually make this work out. Let's take in the ray that's parallel to the axis and the ray that passes through the center. Okay. So hopefully this doesn't get too convoluted. This one will just follow that right on down. This one will coming through there. If I did it right. Oh, that actually looks pretty good. And then trace them back. If you look at just the green lines, I think I did a pretty good job there. They're actually parallel. They're never going to converge on either side of the lens. That's interesting. Mathematically, look at this. If the distance to the object is the same as the focal length, I get a 0 in the denominator. And that is an undefined operation, right? I know how to divide a pie into 2 pieces, into 4 pieces. I don't know how to divide it into 0 pieces. I could multiply it by 0, that I could eat it, right? I don't know how to divide it into 0 pieces. That's an undefined operation. So if you put an object at the focal point, you get gibberish, both physically and mathematically. And if you have a magnifying glass at your disposal, I would recommend that you do this. Hold the magnifying glass up to your face. You see things upright and magnified. Move it back. That is to say, take the object and move it back. At some point, everything gets all gobbledygook. Nothing makes sense. That's when you're passing through the focal point. And then as you get to the other side, of course, what you then see is an image that is inverted and magnified, like this. All right. That is converging lenses in a nutshell. But the fact that I call those converging lenses means that there is another case. So let's look at diverging lenses. Now, diverging lenses is going to look different. If I take the converging lens out of this shape, right? It looks like I kind of cut the converging lens out here and maybe cut another one over here. I get what's called a diverging lens because I've inverted the curvature here, right? If light is coming in from this side, for the converging lens, for the converging lens, this curvature was inverted, which sent the rays to a point of convergence. In this case, the diverging lens will actually bend them away from each other. They will diverge. So this is a diverging lens. So there's clearly not a focal point over here, but if I trace these backwards, they will converge on this side. So I can define a focal point over here and a focal length. Of course, there's one over here because I could just flip this around and put in the light from this side and it would diverge to the left, but I could trace it back and find a focal point to the right. Now, by convention, diverging lenses define their focal length negatively. So if you see a negative focal length, that means you have a diverging lens. We'll see what that looks like in an example right now. Let me take another diverging lens and put it over here. Make sure I stay in frame. Here's my axis. Let me put in a focal point here, and I'll put in a focal point here just in case I need it. And let me put in an object, and I'm just going to do one example here. It turns out that it doesn't make much of a difference if you put the object over here or over here. I'm going to put the object here so that I can get through all the rules. And now I look on my ray tracing rules, which again, if you're in my class, they're in your canvas. If you're not, here they are. A ray that comes in, let me change colors. A ray that comes in parallel to the axis, like this, we see what that does. It diverges in such a way that it seems to come from the focal point. So I'm going to trace that line back, and then this goes off like that. Fair enough. All right, a ray now that passes through the center of the lens is undisturbed. Center of the lens is right there. So on and so forth. And that's all that I'm going to draw. There is another rule. A ray that is heading towards the focal point on the other side is refracted parallel to the axis. I'll do it, but I'll do it in a lighter color because they can tend to get really convoluted. So let me do it in a finer tip pen. A ray that is heading towards the focal point on the other side. So that's right here. So it looks like it's gonna, if I can do this right, this is where a straight edge really helps. Comes in like that, is sent out parallel to the axis. All right, now what would I do with this? I would need to trace it backwards. And looky there, I didn't do that. That's not terrible. This ray, the virtual ray, I should point out, because these are virtual rays in this region where they're converging. Make sure you can still see that. This is a virtual ray here. So I've got a virtual ray from this ray. I've got a virtual ray from this ray. I've got a real ray here. That doesn't matter. They're all going to converge at this point right there. Again, I only need 2 of them to converge to actually see what's happening. I gave you all 3. But it looks like I'm going to form an image right there. And again, it's coming from the tip of the arrow, so I'm going to put my tip of the arrow there. I would usually use this one and this one, but feel free to use any of them that you want. All right, interesting. So, looks like I get a virtual image that is smaller than the object. Let's see if the mathematics bears that out. I'm going to move this up so you can still see it. I still have my thin lens equation, which tells me this: distance to the image is equal to f do over DO minus F. I did not give you values. Let's say that, let's put in some values, see what happens. We'll say that the focal length here is minus 10 centimeters. Remember, the focal length for diverging lenses will be defined negatively. Distance to the object, then, I will let be 15 centimeters. We're going to let that be positive, but the focal length will be negative. All right, so put this in. I get minus 10 centimeters times 15 centimeters over 15 centimeters minus 10. Keep track of your negative signs, which gives me negative 150 square centimeters over 15 minus negative 10 is 25 centimeters. Lose one of the units. What I get out of here is minus 6 centimeters. Yeah, so minus, again, for lenses, in the distance to the image, the minus sign will tell you that the image is on the same side as the object. Check. This is closer to the lens than my focal point, which is magnitude 10 centimeters away. Check. Let's check the magnification to make sure that lines up. Magnification is equal to minus DI over DO. That's minus from here, minus 6 from here, minus 6 centimeters over distance to the object is 15 centimeters. Notice, please, the units go away. The magnification is a dimensionless quantity. I get two negatives make a positive. It looks like what, 2/5? Less than 1, which tells me that the image is smaller, check, than the object. Positive, which tells me that the image is upright with respect to the object. Check. As it turns out, this is a general result for a diverging lens. You will always get a virtual image from a diverging lens. I would invite you to move the object in here closer than the focal length and see what happens. Spoiler alert, not much. not much that's different. But you should do it to see what happens. It'll be a good exercise for you.